very much, Philip. So yeah, as Philip says, I'm from the University of Portsmouth, where I'm a Professor of Intelligent Systems. I'm also one of the theme directors, my theme being Future and Emerging Technologies. And these themes are all about crossing discipline boundaries. So I think artificial intelligence in healthcare is a great example of that. The perspectives I'm going to introduce today will be personal ones based on my own experiences. So I'm going to start with a brief introduction to AI, because I know that not everybody on the call will be very au fait with all the aspects of AI. And they're going to talk about some specific examples that I've been involved with. Two that are to do with predicting outcomes from either surgery or other medical interventions. Another aspect is going to be to do with data quality and what we can do about it. And then my third sort of category of AI in healthcare will be to do with health monitoring. And I'll be pointing out a sort of crossover of discipline expertise from cosmology to medicine. So that's what I'm hoping to cover today. So starting off with what is AI? Well, a classic traditional definition is that it's mimicking human mental faculties with a machine. That's a definition has been, or definitions like that have been long-standing. AI is not a new field. You can argue about when it started, but the phrase itself was coined in 1955 in advance of a conference in 56. That definition defines the challenge, not the technique. So it tells you what AI, the challenge of AI, but not how to tackle it. And it raises quite a few questions in itself. So does the AI need to work like a human, or are you just interested in the output from it? Is indeed the aim to simply match a human, but perhaps in some aspects, the AI can exceed a human, certainly in terms of speed and consistency and reliability. A hot topic at the moment is whether it needs to be able to explain itself. Is it just human intelligence that's relevant, or is animal intelligence also relevant, and indeed perhaps all forms of biologically inspired computing? So there are no right answers to these questions, but it shows that there's a wide range of perspectives about AI. Another key point is that what we understand by AI is evolving. So here's a quote from Rodney Brooks, one of the AI pioneers, who sounds a little bit frustrated when he says that every time we figure out a piece of it, let's say a piece of AI, it stops being magical and we say, oh, that's just a computation. And by example, when I first entered the AI field, building a system that could play chess was considered a significant AI challenge, which was effectively solved in the mid-90s when the Deep Blue beat the Grandmaster chess champion. Similarly, areas like character recognition and speech recognition are now routinely used. They are AI, but they're sort of deployed AI, and we constantly think of AI as being the next challenge rather than ones that we've already achieved. Broadly speaking, AI can be broken down into two families of tools. So in my Venn diagram, the red circle is knowledge-based AI, the blue circle computational intelligence, or data-based AI. And it's that data-based area that's getting most attention at the moment. Very specifically, neural networks are the most commonly used tool for machine learning, where you're spotting patterns in data and using those patterns to recognize new scenarios, typically as classifiers. You train your neural network on a range of different examples, thousands of examples, present it with a new example, and it will be able to classify it. That's the classic example of machine learning. Deep learning is essentially the same thing, except with large neural networks and large data sets. Operational research and genetic algorithms I've also put in there, which are other data-based approaches which are about optimization, essentially. But looking over to the left-hand side, the red circle, there's a long history of AI that's knowledge-based, which takes an altogether different approach based on capturing human expertise in the computer system. And there are a variety of different techniques that have been built up to achieve that. So rules are a classic example. connections between observations and the conclusions you draw from those, and those conclusions can then become the conditions of another rule. So these kind of rules cascade in a kind of logical sequence. And other developments of that concept are case-based reasoning, where you store whole case scenarios and reuse them in new settings. Similarly, model-based reasoning. And then there are some tools which fit in the middle. Things like fuzzy logic and Bayesian updating do have that explicit textual basis, but also have a mathematical model behind them. And these techniques, in my opinion, are not in competition. They are alternative complementary approaches. And I should say, actually, on the knowledge-based side, some of the classic early examples, going back to the 70s or even earlier, were in the medical domain. So, for instance, the mycin system for diagnosing blood disease. The other thing I'd like to say by way of introduction to AI is sort of managing expectations, as I've called it. So I've quoted here from Mike Wooldridge, professor of AI, giving his evidence to the House of Lords Select Committee. And he's managing expectations by saying that there are genuine exciting developments in AI, but these advances have been confined to very narrow domains. And I think that's a very important point. The AI that we currently have, they're all very specific to specific tasks. And the Hollywood dream of conscious machines is not imminent. And perhaps most importantly, he sees no path for taking us there. So the sort of developments that are currently underway are not actually leading to that broad, general human-like intelligence. I mentioned the range of techniques, and that I don't see them as competitive, but actually complementary. To take that idea further, a particular interest of mine is using the whole range of AI techniques in a kind of complementary fashion as multi-agent systems. I'm particularly keen on the Blackboard model, but other models do exist, where it's like mimicking a team of human experts, not just one expert, but a team of human experts gathered around a Blackboard. And this approach enables you to use complementary AI techniques like neural networks, like rule-based systems, like genetic algorithms, all working collaboratively. So that's the broad introduction to AI. I'm now going to talk about some specific healthcare examples that I've been familiar with and working on. So starting with colorectal cancer, this is a collaboration with our colleagues at the Portsmouth Hospitals University NHS Trust. So colorectal cancer, more commonly known as bowel cancer, is the third most common cancer in Europe, second most common cause of cancer death, and cases are rising. The good news is that 90% of cases are cured by surgery, but that surgery comes at a cost, and a large part of that cost, approximately 40,000 euros per patient, is the hospital care. So it would be really useful to be able to predict the patient outcomes in terms of better managing the patient care and making best use of those precious hospital resources. So we've used a machine learning approach to predict 3 patient outcomes: length of stay, likelihood of readmission, and mortality. We've taken an approach based on just under 4,500 patient records, each patient record comprising 47 elements, a mixture of text and numerical type data. And we've used those and analyzed those. First of all, the first stage, in fact, was to analyze those data to see which were the most useful indicators of the outcomes we're looking to predict. So starting with length of stay, I'll just talk you through a handful of them. So you can see here from this kind of analysis, a green bar is good. That means a short length of stay. A red bar is not so good. That's a longer length of stay. So just running through these bar charts, elective surgery is better than emergency surgery. It's better to be young than to be old. It's better to be fit. It's better not to have complications. It's better to have robotic surgery, which incidentally is under the control of the surgeon, but it's to do with the robotic implements. Body mass index is less clear cut, actually, as an indicator. and it's better to have laparoscopic surgery, so through a small hole. So we did that sort of analysis to actually find out which were the important indicators, and we actually did two types of machine learning on this, using our broader set of parameters and just the ones that were found to be most important. So so looking at length of stay, there's a scatter plot here, but maybe I'll point you to the table where we've looked at root mean square error and mean actual error and the accuracy. So accuracy above 80%. We could either use all the relevant input variables, 27 of them, or just the ones that are selected as being most important based on that preliminary data analysis. And the results are almost the same, which is interesting in itself, in that it shows that you can save both administrative and computational expense by just focusing on the most pertinent variables. We've done a very similar analysis for readmission. I won't talk you through the whole bar chart again, but the same principles apply in terms of the sort of factors that favor not being readmitted. So again, the green bar is good, that means not being readmitted. But because this is a binary classification, you either are or are not readmitted, you can present the results in a slightly different way, the so-called ROC curve, receiver operating characteristic, which enables you to present not only the accuracy, but also the sensitivity and specificity. So essentially avoiding the false negatives and the false positives. So the way these curves work is that a good result, high accuracy, high sensitivity and specificity, is for your curve to be close to the top left-hand corner. And you can see we've got some pretty good results here with all three measures above 84%. And the very similar approach with mortality. Again, the green bar is good. That means a longer time window of life. We've looked specifically at the 91 days mortality, which is again a sort of yes/no classification. And again, we've presented it with this sort of ROC curve, and we're getting very good accuracies there, and sensitivity and specificity, all measures above 90%. So these are quite encouraging findings, as I said earlier, enabling better planning of patient care, better use of hospital resources, and better informed patients. So patients can actually know what to expect when they enter hospital, or indeed they may decide under certain circumstances that a long hospital stay is not for them if they're particularly unwell. So these results have recently been published in Discover Oncology. So we're excited about that. It's had quite a lot of interest, and we're planning to grow the study by pooling data amongst some other cancer care centres. And what's really intriguing would be to add the additional photo and video evidence that's available from these operations to see if we can enrich the findings further. I'm now going to move on to a different but somewhat similar application, where we're predicting a different type of patient outcome. In this case, we're looking at dialysis patients to predict a phenomenon called intradialytic hypotension, which is essentially a rapid drop in blood pressure. So dialysis is important. Some 3 million people in the UK alone have chronic kidney disease, many of them on hemodialysis. So IDH, as I said, it means rapid drop of blood pressure, which can actually be fatal. It's certainly uncomfortable and can cause people to actually black out during dialysis. So it's something that if we can predict it, anticipate it, it can then be avoided. So we've taken a very similar approach to that used in the colorectal cancer case. In fact, we found the very similar model, the so-called bidirectional long short-term memory model, to be the most effective. And I'm showing you here the results of our predictor. So not as good, not as clear-cut as with the colorectal cancer case, but still a useful warning of the risk of IDH. Now there are two curves here. The one on the left has the better set of results, and that's a model built on all the data from the data set. So all the test data from the data set, you're effectively using all your data to train the model, and then we've tested it, assuming we have all the measurements. But the fact is that some of those measurements are post-dialysis. So that's possibly a little bit of a flattering measure, because the fact is that as you enter dialysis, you've only got the measurements that apply before dialysis begins. So if you restrict your testing to just having those data available, then the accuracy drops off. It's still useful, but it drops off. And the truth of the usefulness is somewhere between these two extremes, because you can measure some of these patient variables during the dialysis. So during the dialysis, the accuracy of the model moves towards being the left-hand model. I'm now going to take a somewhat different tack and look at health data. And a project that Philip mentioned in his introduction, actually, carried out by a PhD student Obinwa Azonzi under our joint supervision. And let's start with sort of talking broadly about health data. So health data is a massively useful resource. If you think about the UK alone, we have 66 million people. The health information about those 66 million people is a massive resource. If we've got information about their symptoms, their diseases, their medications, their treatments, their outcomes, that could be a fantastic resource, influencing not only their own healthcare, but general clinical practice and health management, etc. The different types of health data sources, but we're specifically interested here in the electronic health records. As I say, there are potentially some 66 million of them in the UK alone. Other forms of health data are available, like clinical trials, wearable devices, etc. But electronic health records are potentially a massive resource, but there is a problem, and that's that they're not as reliable as we would like them to be. And that problem has actually been in the news, both in the UK and worldwide, about the problems of the accuracy of health data records. And those errors come from various sources. They can be from data entry, can be system errors, processing errors, contextual errors, and they affect not only the individual care of the patient, but broad health services, health monitoring, disease surveillance, and so forth. So Obinwa has built this taxonomy of error types, from incomplete health records where specific items are missing, incorrect health records where particular data items have the wrong values, essentially, or maybe the wrong format, and then inconsistent data where the data item itself might appear okay, but it's inconsistent with other data items, so they can't all be correct. And he's built an AI system to spot these kind of errors using a mixture of both the knowledge-based and the machine learning type approaches. So some of the errors are logically inconsistent or out of range. So in this example here, we've got a few data errors. We've got a date of birth marked as 1690, probably a typo for 1960, but out of range. We've got under the gender field is expected to accept both male or female, or M or F, but not masculine, not a blank field, and not a misspelt female. So these are kind of errors that you can pick up with the knowledge-based AI. Similarly, we have what is called contextual anomalies. So here we've got examples where the code doesn't match the observation. So we've got a code 777-3, which doesn't match the systolic blood pressure descriptor. Equally, we've got some measurements here where the units do not match the measurement. Then there are these sort of collective anomalies where things are outside of range for what would be plausible given the demographics described by particular patients or patient groups. So the approach adopted here is a kind of hybrid, a mix of different types of knowledge. So expert knowledge from the clinicians is captured in knowledge-based systems. Likewise, explicit knowledge from clinical guidelines and vocabularies represented in that manner. And then there's discovery, statistical analysis and machine learning from the data to spot what's implausible and out of range. Each of these approaches, as I said earlier, has its advantages and disadvantages, pros and cons. They're not exclusive choices. In terms of those pros and cons, if you look at this map here, if we look at the sort of the right-hand side, we can see that the explicit rule-based or knowledge-based knowledge, whether from dictionaries or indeed from the human experts, has higher explainability than the models coming out of discovery with the more data-based approaches. On the other hand, those data-based approaches are easier to scale and more computable. They're not so reliant on gathering that human input. But on the other hand, turning that back to that sort of explainability leads to confidence. So on the left-hand side there, you can see that the confidence directly mirrors the degree of explainability. So the hybrid approach uses, as I've already really said, the domain experts and the data quality rules from published standards to build the knowledge-based side, and we're using data analytics and machine learning to do the more data-driven side. And Abin was built a practical tool. There's a few screenshots of the sort of things that are presented to the user to analyze these data, ultimately coming up with an analysis of the quality of the data presented with, within this example here, we've got various things to do with dates of birth, dates of death, etc., and the types of error associated with them that have been detected by this AI approach. The last example I want to quote today is work I've not personally been involved with, but colleague Chris Fromeyer and his colleagues from the world of cosmology have been involved with. And I thought it was a fascinating example of the kind of crossover of disciplines. In this case, from cosmology to skin cancer. So navi, or in the plural, in the singular form, a nevus. Nevus is the medical name for a mole on the skin. And these moles are in themselves not harmful, but they do need to be monitored because they can develop into melanoma, skin cancer. And in fact, 60% of melanoma arise from the pre-existing nevus. So sequential monitoring through time of moles or nevi is not routine, but in a way it should be, because what you really want to do is look at those changes through time. And this is where AI and the crossover to cosmology comes in, because this is the sort of thing that the cosmologists are routinely doing. So our friends in the cosmology area working on the dark energy survey are looking at images of some 300 million galaxies using these high resolution cameras pointing at individual bits of the sky. That's why you've got this tiled effect. I'm just going to show you a very short little video clip giving you a sense of how they're zooming in to very tiny features, zooming past galaxies way deep into the cosmos. And finally, you'll see a little bit of toggling of the pixels there, which is the sort of changes they're looking for in these supernovae. They're particularly trying to detect a type of supernova, type class 1a. And what they're effectively doing is comparing images at different moments in time. So here we've got two images, slightly different, at different points in time. They look to the untrained eye identical, but they are slightly different, which you can see if I toggle between the two of them. You might just see a little bit of twinkling, which is just highlighting the differences between them. But that problem of looking for these tiny differences through time is effectively the same as the monitoring of the moles to detect skin cancer. Conceptually, you're doing exactly the same things. You're acquiring the image, You're detecting the sources, that's to say either your supernovae of interest or your moles. And you're comparing how they change through time to classify them as either interesting supernovae, type 1a, or less interesting, or in the medical domain, the good moles, which are not developing into melanoma, or the bad ones, which are. So those were the range of things I wanted to cover today. To bring it to some sort of conclusion, hopefully I've shown you that there are a range of AI techniques, most importantly, neural networks and other techniques for machine learning, finding patterns in data, rules, cases, models for more explicit knowledge representation, and other techniques also exist. There are a wide range of potential benefits for AI in healthcare. I haven't covered them all, but here are some of them. Diagnosis, haven't really looked at today, but is a key area for AI. Treatment and care, which I have looked at today in the areas of colorectal cancer, predicting patient outcomes, and also trying to flag the risk of intradialytic hypotension in dialysis. Looked at health monitoring in the case of skin cancer. And I also haven't touched today, but is also a really interesting area, is independent living, using AI to monitor the well-being of vulnerable people and to assist them. Also looked today about the issue of health data quality, where the quality of data, or the rather poor quality, can be a problem for AI, but perhaps AI can offer a solution in monitoring, spotting the errors and on offering solutions. And the final point is to sort of echo the quote that I used right at the start from Mike Waldridge, that AI is really good at specific, narrow, repetitive tasks. So I think it's got a really important role in supporting clinicians. There's no imminent future, I think, in actually replacing them. I'd like to acknowledge the support of various colleagues who've worked on these projects, rather. All of them I've been involved with, apart from the last one, which was one from my cosmology friends. I can't finish off without a plug for my book, which is just out in its 4th edition, Intelligent Systems for Engineers and Scientists. And that is supported by some tools about AI and information about AI on my website at adrianhopgood.com, where you will also find a discount voucher for the book. That's all from me. Thank you very much for your attention. And I will hand over to Philip.
Thank you very much, Adrian. That was a fascinating presentation. If you could just take it on to the next slide, please. I'm just going to kind of complement Adrian's presentation with just a few closing thoughts about the ethical questions which perhaps arise when we think about the use of AI techniques in health and care. And just to start with, the fundamental concept here is this principle of precaution, first do no harm, from the Hippocratic Oath right down to today, of avoiding harm by an intervention which is designed to do good. So let's move into the list of possible issues to consider. And this is by no means comprehensive, but maybe some of the key issues to consider when thinking about applying AI methods in health and care. So the first one, and perhaps the most well-known one, is bias. So what is the data that the AI model or tool has been based on? How fair is the data? There are very often examples where the data sets that are used are not truly representative. They may be biased by gender, they may be biased by ethnic group, they may be biased by geography. So we have to just question how fair the data is that's being used, but also the analysis. Sometimes AI techniques such as supervised learning rely on labeling the data, which is a human task. And that can be subject to all sorts of human bias and cognitive bias that come into how data is identified. And then sometimes there's a more subtle bias in the data in terms of access to healthcare services. So we know, for example, that in countries where access to healthcare is based on insurance and personally financed healthcare, then socioeconomically disadvantaged people are excluded from the data because they just don't have access to the healthcare service, and therefore their data is not part of the data set. Perhaps more subtly, even in this country, we know that certain ethnic minorities are prone to underuse health services for sometimes subtle cultural reasons. And so again, their data is missing from data sets. Moving on to the next point, Adrian mentioned explainability. So if we're thinking about a black box algorithm where there's some incomprehensible multi-layer kind of neural network analysis, is that kind of prediction really compatible with informed consent if nobody can understand how the conclusion was arrived at? The next point is about trust. So related to that, when we think about the fact that AI is largely about retrospective analysis of data, it's not largely about prospective trials. And so it doesn't have the same methodological reliability in the sense of accounting for confounding variables. So there are a small number of AI trials that have been accompanied by prospective research, but by and large, it is retrospective. The next point is around validation. So if it's very perhaps simplistic to look at something in a laboratory setting or in just a desk analysis setting, but has the model been validated in a real world setting? So where you're not looking at just at some sampled piece of data, but where you're looking at actual real world variants. The next point is around professional autonomy. So are the if perhaps this is implemented into a level of decision support where there's some predictive suggestion of guidelines or suggestion of actions or actions to avoid, is that perhaps constraining? Is it putting too much guidance in the way of a clinician? Moving on to safety and regulation. So in this country, we have the Medicines and Healthcare Regulatory Authority. So they have to authorize software that is used as a medical device. So has that been followed? And even if it has, is that in itself sufficient? An interesting paper I was reading recently made the point that in the US, where the FDA, the Drug Administration, similarly authorizes AI applications, there were 130 FDA-approved AI devices, but 126 of them were only based on retrospective studies. And of the 54 of them were classified as high risk, and none of those had prospective studies to support them. So again, sometimes we need to even question whether the regulation is good enough. Moving on, expectations. So Adrian mentioned this too, expectations of what AI is, but it's also expectations of what AI can do to change things. So it may well produce a more rapid diagnosis, but is that actually going to make a difference? Or does it just mean that it's raised expectations, but people still have to wait just as long for the actual treatment? Are we actually making a change at the right point in the delivery of healthcare services? So a few things to think about. So it's by no means saying we mustn't touch AI, it's a bad idea, but it is saying there are serious ethical issues. And as professional bodies, we do need to be making people aware of these things to reflect upon as they think about introducing them into the delivery of health and care services. So moving on, we come now to our question and answer session. We've had a few points raised in the chat. Before we go to that, if we could just look at the learning outcomes. So hopefully by now you can at least give an outline description of the range of tools that are used to build artificially intelligent systems. The next one is to provide examples of how machine learning can be used for health monitoring and predicting patient outcomes. Next one is to describe some of the difficulties in using electronic health records for machine learning, and then to consider the ethical implications of using artificial intelligence and machine learning. So then after this session, we're suggesting some questions for reflection. So as this is designed as part of a continuing professional development series, we'd like you to reflect on these questions. So can you name at least 2 tools that can be used to build AI systems? And the next one, can you provide 2 examples of machine learning for monitoring health or predicting patient outcomes? Next one, can you describe 3 types of error in electronic health records that can affect machine learning? And finally, in your own professional setting, whatever that might be, can you give at least 1 example of ethical questions you would need to consider before applying AI within your own professional setting?